So, after enumerating things like variances, etc., or basing them on enumeration, after using algebraic calculations, from which we can learn a lot of things in general properties, now the point comes where we say, what can we do in the only realistic fashion in a real sample? A real survey means one sample and one sample only. So what can we then do? We cannot enumerate, we cannot calculate, because for that we need information on all units. We don't, which is why we leave behind the calculated column in practice. It's not that it's useful, it's useless, sorry, it's not that it's wrong, but we are going to use the estimated column. Well, let me take that back again. And then you see that the population variance here is calculated, because you cycle through all 10 million units. Here only to 10,000 units, but what we say is, well, this is a pretty good substitute for that. It gives us a pretty good idea. And then for the total, the formula is the same, except that it gets a hat on. We have estimated this quantity. Of course, if I take a new sample, I throw away my sample and I start again, S squared y will be the same, because it doesn't depend on the sample. It only depends on the population as a whole. But here, yes. I do away with my sample, I start again, and what I will get is a somewhat different value. Again, if my sample is large enough, it may stabilize, and that may not be so bad. Otherwise, yes, there may be substantial differences. Okay. And then for the total and for the averages, it's of course the same. You take the population quantity and you scale it up or down. So the factors you multiply in front are different, as I said. It's just that the calculated quantity is no longer considered feasible, and we will use the estimated quantity. Okay. Let's see what it really means in practice. Take a sample of size 2 from the artificial population. That's easy to do without replacement. We have only 6 of them. So these are the 6 samples. The calculated variance is 6.6667 all the time, because it only depends on the population, not on the sample. So it's immaterial, it's irrelevant that I even put it next to a sample. It's always the same. However, the moment we're going to estimate it, it's 0.5, it's 4.5, 0.5, etc. So the S squared y is going to be changing the sigma square y hat. So the estimated variance of the estimated total is going to change indeed. One is 4 times the other. That's why I have that intermediate value. So rather than calculating the true 6.66667 all the time, I get it correct only on average. But for my particular sample, and this may be disconcerting, I may get 18 or I may get 2, depending on the sample that I take. Simply, there's no bias, because on average they're correct, but simply because the sample is so small. And this tells me that, the precision that we get, the standard there, we should really tell that to ourselves, is not the true population value. It's an estimated value. And that in itself can be fairly imprecise. And that's why a large sample, or a sample that comes close to the population quantity, is important. Okay. And then for the covariance, just to round off, it's exactly the same. For the covariance, you replace the population quantity, which is capital N-ish, by the sample quantity, which is lowercase n-ish, and changes from sample to sample. Okay, that brings me to the end of the analysis chapter. After the design chapter on simple random sampling, in this part 2, there's one more thing to do, and that is sample size determination. But that's the topic of the next chapter.